Hello everyone, today we'll start our first experiment in Design 2 Lab, Control Lab. So this will be our DC motor control. So basically what do we have? We have a DC motor. As you see, this is the motor and this is a disc coupled with the DC motor. And what we have also, we have our control unit, and basically we're sending signals between the hardware and also the software in order to control the speed of the disc. So in order to control that setup, we need to go into our computer and open my computer, disk D, and we look for DC motor experiment, DC motor, and here we have the software because we need to send signals from the controller into the hardware. And basically today we start with the first section, which is DC motor modeling. If I double click this, lab view software will open, and what do we see in here? So basically we have multiple devices. What device that I want to control right now? So if I select this, I find that automatically the computer is now connected with device number 2, so I select device number 2. If I run this system, automatically if I send the signal to run the system, automatically the hardware, it will run, as you see. So run. So now you see the DC motor is rotating, is working, and you see this on and off, square wave, on and off, on and off. It will continue. This is 10 seconds, so we can control the time limit from 0 instead. So I see from 0 up to 20, for example. We have two screens. This screen for the output, which is actual motor speed, and the simulated motor speed. So this is output of the DC motor. Meanwhile, we can see the input, which is the voltage. So I'm feeding the motor with a voltage of a square wave, sometimes 0 and 1, 0 and 1, on off, and based on that I'm seeing that the signal of the speed is also fluctuating on and off. So what else do we have in this screen? We have our measured speed from the sensor attached to the motor. It's showing now 1, now 70. So this is a digital scopes only to show the value of the speed, while in here we can see actual speed, the same measurement. Digital scope for current, we cannot see current in this figure. Digital scope for voltage, it's about 1 now, right? 1, 3, 1 and 3, 1 and 3. So how I can control the signal, how I control the speed? So obviously what I have, the purpose of this experiment, it's modeling. I want to model, I want to find a model. You see this blue signal, the simulated motor speed, it's far away from the actual value of the actual speed. So our objective is to find some model, find the gain k and the time constant tau. You see this is k and this is tau. If I'm able to find those values of k and tau, then maybe I will generate some model to perfectly match the values of actual speed. For example, let me just try by luck. I'll try maybe 28. Done. See, now you see that our model is pretty much close to the actual value, but still I need some enhancement on this k and tau. So our objective basically is how to find the model. This is modeling, model of the DC motor to match the actual value. So what is this? What's amplitude and frequency? So we are giving an input signal of a volt. This is voltage. This signal, it has an amplitude of 1. If I make it 2, for example, that means I'm feeding higher voltage. That's why the DC motor speed is higher. If I make it 3, for example, I will have higher speed. I can control this to 250, for example. So this amplitude controls the value, this amplitude controls the values of voltage in here. If I go back to 100, you will see that I have different values of voltage based on the amplitude. What about frequency? Frequency is how many cycles per 1 second, how many cycles of voltage we are seeing. So let's start from 150. If I say that frequency is less than this, 0.4, no, I'll make it 0.2, for example. Enter. So you see that you have less frequency, you have less repetitions. If I make it, for example, 0.1, you have more time in this cycle and then more time in that cycle, and this is how I control the frequency. If I make it 0, means what? I don't have any repetitions, so the speed will be fixed at that specific value, and the the voltage input, the feed voltage will be constant at that value. So 0.2 for example for the frequency. If I just want to stop for a second, let me go back for the normal values 10 and 2 and 0.2. It was 0.4. Let me just stop. I will stop. So how we are going to perform our experiment? Basically, if you go back to the folder of the DC motor experiment, this was the DC motor, this was the softwares, and now I'm going to start the manual. I have 3 manuals, one student manual and one guide manual and one user manual. For student manual, if you open the student manual for DC motor experiment, we will have this manual. So it's basically start with an introduction of the experiment. Yes, it will start with an introduction to the experiment. It shows the details, the names, for example, the screen. When you open that LabVIEW software, what will see? You will see something 12, 11, 1, 2, 3, and then shows how we are going to understand those elements. So for example, the device number 11 means the device, so we go back to the photo and see number 11. That means we need to select the device as we did. So we can just go through this manual. It's available in Blackboard, and then in page number 12, this is our in-lab experiment, and section 1, the modeling experiment through pump test model. So this manual offers a very nice and step-by-step instructions on how to perform the experiment. So step number one is we need to open our software for modeling. We already did that. It's available in our LabVIEW. This is our modeling software. Good. Number 2, we need to select the proper device. We may need to make sure that the proper device is chosen, and that's why we did that. We select device number 2, the one connected to the computer. Good. So if we run the modeling software, the actual motor should begin spinning, and scopes on the VI should appear similarly. So we have it. When we run the software, we have our actual input and output simulations available. Stop. Good. So now if you want to start, now we have the instruction to put the amplitude into a specific value, amplitude 2 volts, frequency 0.4 and offset 3 to 0.4 and offset 3. Good. So what else? Once you have collected a step response, click on the stop button to stop running the VI. So this is not enough, so we can say that we want to study only 10 seconds. I will make this 10 seconds. When I run, so I will start, this is 3 seconds, this is 5 seconds, this is 8 seconds, and this is I just stop. So this signal, this sample is enough to study for us. So this is exactly what he said in here. So if we are collecting some data, you click the stop button. So now we have some questions or exercises. Number 1, we need to attach, when we make our report for this experiment, we need to attach the response of this speed and voltage graphs. And basically, and very simple, we can go and snipping tool, we can take a photo of this response, and we say that this will be our output and input. So this is input in volt, time and volt. This is output, speed and time and speed. While this output curves, they have both simulated speed and actual speed, and we see that there is a big difference between them. That's it. So now we are done with exercise number 1. We are going to have some instructions, preparation for exercise number 2. So if we select the measurement graphs, we can view the measured responses. So what is the measurement graph? For example, if I ask you now, what is this value? What is the peak value of speed? Is it 150, 149, 148? What is the exact value? It's difficult to measure this value, and that's why we have our measurement graphs. Measurement graphs have this tool, so this line, this yellow line, I can move up and down, and just I can stop in the middle. So this is cursor number 0. It shows a value of 147.32 in y-axis. That means the highest value, the peak value, is exactly 145.536. Same time, I have this vertical axis, vertical lines, in order, for example, if I want to take this loop, this cycle, so this cycle starts at this time, which is exactly, this is cursor number yes, cursor number 0. When I move, it moves. So the x-axis value is 1.59, and this it reached the top. It reached this level at specifically 2 point something, which is 2 point. This is cursor number 1, exactly at 2.03. So measurement graph, it shows only, it helps us to measure the exact amount of time or speed or even voltage, because this is 5 in here. We see that it's 5. So for exercise number 2, we need to use the responses for speed and voltage in order to compute the steady state gain of the DC motor. What is that gain? We know that gain is this amount of K, because the first order system has a transfer function of K over S plus tau, where K is gain and tau is a time constant. So tau is time constant, K is the gain. So let's go back to our manual. It helps us because it said that make sure you fill out table number 5. If I click table number 5, it shows me the elements that I need to calculate my value of K and tau. To find K, we need to find our omega, the speed, steady state speed. We need to find our initial omega, initial speed, and we need to find our voltage, amplitude voltage. So 1, 2, 3, from these 3 parameters I can find the gain, the steady state gain. Same thing for tau. In order to find tau, I need to determine the decay speed and something called initial time and decay step time. What is this? What is T0, T1, omega 0, AV? So if you go back to exercise number 2, that's it. So it helps, it says that see the bump test method section in practical control guide for details on how to find the steady state gain from a step response. So what is this practical control guide? You remember when we say that we have more than one manual? This manual for a student to perform the experiment. This practical control guide offers information, theoretical information about the device. So if we go to content, and as advised by the manual, it said that go to bump test method section. So this is modeling, and this is bump test method in page 34. Let me just write that 30 something. So if I go down, motion control, yes, motion modeling. So this is the general transfer function of K, of the first order system. K over tau S plus 1. Tau is time constant, K is the gain. This is the bump test method. Basically, we have an input U and output Y. So we know that our input is going from U minimum, 0 for example, until suddenly U maximum. This is delta U, U max minus U min. At the same time, we have our initial Y, initial output, Y0, initial speed in our case, and then gradually it moves into the steady state Y, steady state output. And you know that that's okay. I'm sorry.
Slipped.
I'm sorry. So we know that to find time constant is the time needed to reach 66%, 63%. So this time will represent the 63%. So we have the formula in here. So in order to find the value of K, the gain, we need to divide delta Y output divided by delta U input. What's delta Y? This is delta Y, maximum Y, steady state Y divided by initial Y. This is delta Y. What's delta U? The input. Y, U maximum, U minimum. If you divide those values together, you will get K. So delta Y is easy, Y steady state minus Y0, delta U is easy, U max minus U minimum. If we go back to our manual, student manual, now in table number 4, you see now you have our steady state value, our U initial value of speed, we divide them, delta Y, and we have our amplitude for voltage. If we divide these values divided by the same as the formula, we will get our KB. How we will do that from the LabVIEW screen? So we will measure the highest omega steady state, and we will measure also the minimum omega, the initial omega. This delta, this difference will represent our delta Y. What about input? The minimum voltage is 1, the highest voltage is 5. That means we're talking about 4 voltage difference. So we divide that speed, the other manual, we divide speed difference divided by voltage input difference, and we will get our value of K. That's it. What about tau, the time constant? Same thing. We need our decaying speed, and we need to find something initial time and T1. What's T1? What's T0? T0 is the start of the motion. T1 is the time equivalent to the time constant, and we can find this time by finding y1, y of T1, which is 63% of the steady state. So first we need to find y1. What's y1? Y1 is 63% of the steady state, of course, plus the initial y. So starting from 0, this is initial y, and then you are adding 63% of the steady state. You get this value. If you get this value, you take the cursor and then stop at this point, the intersection, and you go down to time axis to read the value of T1. This is T1, this is T0, and that's it. So if we go back to our screen, I'm talking now about y-axis. Y-axis, this is, I select this cycle. This is T0, which is 1.56. In order to find the value of T1, I need to find that T1 from the equation, which is approximately, it will be around this 63% of that. So it will be around this value, and then I need to take my cursor into this intersection point, this one, and then I will say that the difference is 1.7. 1.76 for T1, 1.56 for T0. Delta T will give me the equation. So in order to find tau, the time constant is simply the difference between T1 minus T0, and that's how we can find our time constant. That's it. So if we go back to exercise number 2 and 3, exercise number 2, find the steady state gain. Exercise number 3, make sure you complete the table, find the time constant, K and tau. So we are done with this. By calculation, we will get the values of K and tau. For example, by calculation, we say that it is 25, for example, and tau is 0.17, for example. Now if we run the system and we go back to scopes, we will find that our calculation, theoretical calculation, doesn't match the actual system. That means our model is not accurate enough in order to predict the motion of the actual system, and that's why we do something called model validation. So model validation means simply we need to just manually tune the steady state gain and K, tau, both of them, in order to find the perfect matches between the actual and the theory, model and actual. So here now for validation, I'm just increasing the value of K a little bit, Okay, a little bit more than that. Okay, it seems matching right now. What about tau? Tau control the x-axis, the time axis. So if I reduce this, let's see. Okay, it seems good. If I reduce this, still okay. That seems good. So the rising is perfectly matching, and now I'm done with the modeling. So that DC motor in the screen you see, it has a model of first order system k over tau s plus 1, where the value of k is this and the value of tau is this. And this is simply the first experiment of the DC motor, which is about modeling. So this is 5 exercises, and if we go further, we will find that we can also do more than modeling. So if I just stop this and I go to that folder, the folder of experiments, VIs, I can find that more than only modeling. For example, I can find speed control. If I open speed control and same thing, I select the proper device and run the experiment, we will show that we have a specific signal, the reference, the desired value of the DC motor. Let me just move this to 30. So we have our reference and then we have our measured. This is different than modeling. So now I'm controlling with the BI controller proportional and integral values of gain in order to control or to give specific voltage in order to have that matching between reference and actual. So next time we will learn how to control the P parameter and I parameter proportional and integral gains in order to have a perfect matching. For example, if we look now at instead of 0.5 I make it 0.9, we will find that I have deleted that overshoot. That means if we increase the KB, the value of overshoot will decrease. So if I just make it 0.2, you find that we have high overshoot. So we will do it next time, the speed control. For now, just we need to concentrate on the modeling exercise, and you will find in Blackboard all manuals, the student manual, the control guide and everything. And thank you.